Hello, welcome back to AE 2220 Dynamics. In this video, we are going to start our discussion on impulse and momentum, quite literally just starting with impulse and momentum. So we're going to recall that the linear momentum of a particle is defined as, and we use capital L to represent the linear momentum, and it's a vector, is equal to the mass times the velocity, again a vector. And then we can write Newton's second law as that the sum of the forces, the vector forces, is equal to the time rate of change of the linear momentum, or the time derivative of that linear momentum. Now, if we go ahead and we multiply both sides by dt, and then we integrate from some time t1 to t2, we'll find here that we'll get that the sum of the integral from t1 to t2, and we can switch the order of the integral and the sum because these are linear operators. So we get the integral of f dt equal to m r dot at t2 minus m r dot t1. And this integral, or the left-hand side here, this is called the impulse. And we're going to write it as imp 1 to 2. And it has units of Newton's seconds, or force times time, so pound seconds, pound minutes, whatever you're considering. We're going to see in a moment later what an impulsive force is, an impulsive motion, and we'll discuss more about what that really is. We're going to also shorten the right-hand side. We're going to drop the function notation, and we're going to say that this is m r dot r2 dot, and over here we'll say that this is m r1 dot, and that will just save us from having to write this function notation. So then the impulse is defined as the sum of the impulses, and I guess actually let's come back up here where we were just at, and the impulse is really the integral. It does not include the sum, so it's my mistake for drawing that like that. So the sum of the impulses from 1 to 2 is equal to the change, but not the time rate of change, just the change in the momentum, the linear momentum, r2 dot minus mr1 dot. So mr2 dot minus mr1 dot. Or, rearranging, we can write this as mr2 dot is equal to m1 dot plus the sum of the impulses from 1 to 2. And this equation, this here, this is the principle of impulse momentum. Principle of impulse momentum. So the final momentum is going to be found vectorially by adding the impulse generated by all external forces and the initial momentum. And if we're dealing with multiple particles, then we can just extend this further. In that case, we'll have that the sum of the linear momentums, and we'll write this as the sum, and we're going to use I to represent each particle, so mi times r sub I2, where the I2 represents r dot I2 represents the velocity of the ith particle at time t2, and this is going to be equal to the sum of mi r I1, r dot I1 plus the sum of the impulses from 1 to 2. And so what happens if there are no external forces? Take a moment, pause the video, think about this, and then write down your answer and what you think happens. And then come back and we'll compare with what the answer actually is. Okay, welcome back. So we're left with what if there are no external forces acting on the system? Well, if there are no external forces acting on the system, then the linear momentum is conserved. So we'll just say here, if there are no external forces, then the linear momentum is conserved. And so we get here that the sum of mi ri2 dot is equal to the sum of mi ri1 dot. All right, so we're now ready to move on to discuss impulsive motion. So impulsive motion involves a force that acts at a very short time, but is very large. So just to read what we have here, we can say that a force acting on a particle during a very short time interval, but large enough to produce a definite change in momentum, is called an impulsive force. And then the resulting motion is then called an impulsive motion or an impulsive response. So some examples of impulsive forces are things like a bat hitting a ball, or a hammer hitting a nail, or in my research, we use instrumented hammers to hit structures to cause them to vibrate. So that is an impulsive force as well. And then we measure the impulsive response of our structure. So we're talking about these very short duration but high force or high amplitude forces that then cause the system to have a definite change in momentum. So impulsive forces persist for a very short time interval. We'll say delta t here, but the average force over that duration, that interval f sub average, is very, very high. The resulting impulse then is f average multiplied by delta t, and the principle of impulse momentum is going to be m r2 dot equal to m1 r1 dot plus the sum of all of the impulses f av times delta t, where of course there may be multiple delta t's, and this is for a single particle, and for multiple particles this becomes the summation of mi ri2 dot equal to the summation of mi ri1 dot plus the summation, and really we should have two summations here, so I'll put that in here because we're summing over both all of the impulses as well as all of the particles. So we get plus double summation f average, and we'll add, in fact, let's get rid of the average. Let's just add an I here, f average, delta t, ti. And that is what it is for multiple particles. And with that being said, I'd just like to go back up real quick, give you a moment to catch up. We're going to go back up and we're going to go correct what we had up here, where this should be the summation of, should be a double summation, because we're going to sum over the particles, and we're going to sum all of the impulses. So we'll just add an I subscript here. So we're going to sum all of the impulses from 1 to 2 acting on each particle. All right. We're now going to look at our solution procedure for solving problems with impulse momentum. We're then going to go through an example problem, and then we'll go through impacts. Okay, so for solving impulse momentum problems, we're going to start off by defining a coordinate system. We're then going to define position vectors, and then we will determine velocity vectors before and after the impulse. We'll then compute linear momentums and impulses, and from there we'll go and apply the principle of impulse momentum and solve. And so the kinematics is going to be the same as what we've been dealing with throughout this entire class. So everything that you've learned previously in terms of finding coordinate systems, position vectors, velocity, acceleration vectors, etc. Although we don't need acceleration vectors here, we just need velocity. But all of that is the same, which is why we start with that in the beginning. So we're going to go ahead and apply this solution procedure to an example. This is example 3. We are told that a package slides off a ramp and impacts a cart beneath it. We're asked to determine the velocity of the cart after the impact and the impulse exerted by the package. We're asked to then ignore gravity, and then I've gone ahead and I've split this into two parts. First, we're going to find the final velocity of the cart, and then part B, we're going to focus on finding that impulse exerted on the package. All right, so we're going to start by defining a coordinate system. In fact, we're going to need 2 coordinate systems in this case. I left them drawn on your diagram. In this case, I placed my origin. I'll add the little O for the origin right here. I've placed my origin there at the tip of the ramp, and then I've drawn where the package is and given it dimensions in purple, and its displacement is measured with Rp of t, and the displacement of the cart is measured with Rc of t. And since we're going to treat these as particles, we don't necessarily need to know where the center of mass is, so I've just assumed where it is on the cart, and I've assumed it's at the center of the package itself. So I said that we're going to define 2 coordinate systems. First, we have, we're just going to write here Cartesian with the origin at the end of the ramp. You can pick any origin you want and put your coordinate system anywhere you want. This to me was just convenient, primarily because it allowed me to define 2 Cartesian coordinate systems and leverage the angle of the ramp as well to relate them. So I'm going to go ahead and draw my 2 coordinate systems. First, we're going to have the I direction. That goes horizontal. Then we're going to have here the J direction. And let me try drawing these a little bit more to scale. So that's our I direction. This is going to be our E2 direction. And then down here, we're going to have our E1 direction. And we know that this angle right here is theta. This angle here is theta. All right, so we want to now define E1 and E2 in terms of I and J, and we're going to do the same thing for I and J as well, defining I and J in terms of E1, E2. So first, well, let's do E1. So what we're going to do is we need to imagine that E1 here is forms the hypotenuse of a triangle, as shown with this orange line. And then we can see here that given the angle theta, we're going to end up with a cosine term in the I direction. So cosine theta I. And then in the vertical direction, we're going to have sine theta j, and it's going to be in the negative direction. So minus sine theta j. And then for E2, we can do the same thing. We draw a little triangle, or make E2 the hypotenuse of our triangle with that little orange line there. And you can see here that now we're going to get, in the I direction, we're going to get sine theta. Let me switch back to red. We're going to get here sine theta. It's going to be in the positive I direction. And we're going to get cosine theta in the j. So it's very common that these, the cosine and sine will switch order, and there will also be a change in the sign as well in front of the sine theta term. So you can see here we have a negative sine theta in the j direction, and that will mean that for the E2 component, we're going to have a positive sine theta in the I direction, and since we have cosine theta in the I direction, for E1, it's going to go down into the j direction. This is very, very common, and you'll start to notice this pattern the more you do this. To the point that once you know which one has a negative in front of it, you'll know once you know what the sign is in front of the sine theta term, you'll be able to determine what it is in the next one. All right, we're going to do a similar thing here for I and j. So we're going to draw I here, and we're going to say that I is now the hypotenuse of our triangle. And we'll draw a little line in scion right there. And so in this case, we're going to end up here in the E1 direction. We're going to have cosine theta E hat 1. And in the vertical direction, or the E2 direction, actually, we're going to have plus, because it's pointing in that direction, plus sine theta E2, E hat 2. Now that I know this, we can actually we're going to write here minus sine theta E hat 1 plus cosine theta E hat 2. And then let's go and check if this is correct. So we're going to come in and we're going to pretend that j is the hypotenuse of our triangle. Let me try and align that. It's good enough. So we're going to get here in the E hat 1 direction, it's going to be the sine theta component, and it's pointing in the negative E hat 1 direction. So we are going to get minus sine theta E hat 1. And then we'll see here that it points in the cosine, that in the E hat 2 direction, it's cosine theta and it's positive. Okay, so now that we have a relationship between our coordinates, I'm going to go ahead and just erase those lines there just to leave this and make this more clear. From here, we're going to go and determine our position vectors for each object. So first, we're going to start with our package. We'll say MP here. And at its current position, we're going to say that RP, the vector, is equal to, in fact, I didn't draw my position vectors. So let me go and do that. So this is RP, and we're just saying going down here, this is RC for the cart. So RP in this case, we're going to do it in the E hat 1 direction. And we need to add a little bit here. We can call this dimension Q. So we're going to get here that this is in the E hat 1 direction. It will be A plus RP E hat 1 plus Q E hat 2. Okay, so we're going to now expand this into I and J coordinates. So we're going to get here in our I direction, we're going to need a square bracket A plus, let me write that a little bit better, A plus RP cosine theta plus q sine theta, all of that in the I direction, plus in our j direction. We're going to have here minus a plus rp sine theta, and then we should have plus q cosine theta, all of that in the j direction, and that is for our package. Now for the cart, MC, we're going to have here RC equal to Q plus hold on a second. This should be, it should be B. I'm not sure why I have Q in my notes. Should be B plus RC. That's a function of time in the I direction minus HJ. Okay. Now that we have our position vectors, we can go and find our velocity vectors. We're going to do this before and after. So we'll start off with before, and we can just go and compute velocity vectors, but we also want to think about what happens before and after. So you have two choices. You can just go and compute the velocity vectors prior, but prior to considering what happens before and after. But the thing is that those velocity vectors may change, and they may not be the same after the impulse. And as a result, deriving them right away can lead to things being incorrect. So we're going to stick with doing them before and after. So for our package, this, we're going to go and compute our derivative of this RP. We're going to say this is RP1 for time t1. And then taking the derivatives here, cos or theta is constant, q and a are constants. And so we're going to end up here with simply RP1 dot cosine theta in the I direction minus RP1 dot sine theta in the j direction. So for the cart now, we can go and compute our general velocity vector RC dot. Let's see, RC1 dot. This is just going to be RC dot in the I direction, C1, and this is equal to 0 I because the cart is not moving at this time. The cart is at rest. We take a look at after now. In this case, the package and the cart are now going to move at the same speed. The package stays on the cart and then it moves with the cart. So package and cart move at the same speed. Move at same speed, we'll just say. So what this implies here is that for our package, RP2 dot is equal to RC dot in the I direction. And for the cart, MC, we're going to get here that RC dot is also equal to RC dot in the I direction. And we don't know what that is yet. Okay, now we're ready to go and compute our linear momentums and impulses. So what I'd like you to do is pause the video and go and compute the linear momentums in the beginning at time t1 and then at time t2 at the afterwards. Go and compute your linear momentums. Don't worry about the impulse. We'll come and do that together. But pause the video, take a look at compute those linear momentums, and then when you come back, I'll go through it and you can compare with what you did with what I got. Okay, welcome back. So we're going to go through and compute the linear momentums now and the impulses as well. So we'll start off with L1 here. So it'll be equal to the sum of the masses times the velocity vectors at time t equals 1. This is going to be equal to mp times rp1 dot plus mc rc1 dot, which we can write this then as mp times that's not a vector anymore, rp1 dot cosine theta I minus rp1 dot sine theta j plus mc times 0. So that's just going to go to 0. And then we'll find that the linear momentum L1 is equal to mp rp1 dot cosine theta, the I direction, minus mp rp1 dot sine theta, and that's acting in the j direction. So then for L2 here is going to be equal to the sum of masses times their velocity vectors at time t equals 2. Okay, so we can expand this out, and we're going to get that this is equal to mp rp2 dot plus mc rc2 dot. So it'll be equal to mp rc dot I plus mc rc dot, also in the I direction, and then our linear momentum L2 is going to be equal to quantity mp plus mc times rc dot, not a vector, just a scalar, in the I direction. So that's our linear momentums. Take a moment and compare what we did here with what you did. And where did you make a mistake? Did you get the same answer as what I have here? Take a moment, just reflect on what you did and how it went. Okay, we're now going to go and we're going to determine the impulse acting on each body, and we now need to draw a free body diagram. So one thing I have noticed when looking at your homeworks and worksheets is that a lot of people are not very careful with how they draw their free body diagrams. And it's very important that you draw and place the forces at an accurate location of where they're acting, rather than just drawing them wherever you want. This is going to be particularly important when it comes down to rigid bodies, where we will actually need to know where they are acting on the system, and just drawing them at any location is going to lead you to getting the wrong answer or creating an incorrect result. So it's very, very important that we draw our free body diagrams accurately, and we put the forces both in the correct direction as well as at the correct location of where they're acting. So that means drawing the mass or the weight or gravity force at the center of mass of our object, and then drawing where we have reactions where they're placed. So in this case, we're going to have on the package, we're going to have two impulses acting on it. First impulse we're going to draw, it's going to be acting horizontally, and it's going to be acting at this corner right here, and it's going to be going in the negative I direction or negative horizontal. And we'll say that this is fx delta t. So here we're really drawing our impulses, but It serves the same purpose as a free body diagram. And then pushing up here, there's going to be some Fy acting at delta t, or times delta t. On the cart, we're going to have equal and opposite impulses acting on this system. So we're going to have Fx delta t here, and pushing down, we're going to have Fy delta t. And then in addition to that, to resist this downward impulse, the ground is going to push back up, and we're going to have some R1 here, delta t, and an R2 delta t. So then our impulse, the impulse then, we do this for each mass. In fact, we'll say the impulses are for the package, MP, we're going to have here the impulse from 1 to 2 is going to be equal to minus Fx, and we'll put a little p here for package, minus Fx delta t, I plus Fy delta t in the j direction. And then for the cart, or MC here, we're going to have that the impulse, imp 1 to 2, for the cart is going to be equal to Fx delta t I plus R1 plus R2 minus Fy delta t. And that's in the j direction. So we're now ready to go and apply the principle of impulse momentum to determine the final velocity of the cart. What I'd like you to do, well, actually, before you do anything, I'm just going to give you a little bit more insight into this. So this impulse is acting internal to our system. If we consider what we're going to do is we're going to consider the motion of we're going to consider our system to be the combination of the package and the cart. We're going to consider them both to be our system. And as a result, the impulse is then internal to that system, and we can neglect it for right now. And then in part B, we'll go and consider the package by itself, and then we'll go and compute that impulse. So let's just write this down real quick. We'll say here that the impulse is internal to the system, so we can neglect it for now. With that in mind, I'd like you to go and apply the principle of impulse momentum and go and determine what the final velocity is of the cart. And this will only be in the I direction, and that's because any of the vertical momentum will end up being absorbed by the ground. So go ahead, pause the video, work on this, and go and determine what that final velocity is, and then I will come back and I will solve this, and then you can compare and reflect on what you did versus what I did. All right, welcome back. So I asked you to go and compute your linear or apply impulse momentum and then determine that final velocity. We're now going to go and do that here. We're going to start by recognizing that if there's no impulse acting on it, then linear momentum is going to be conserved. So in this case, we will have that L1 must be equal to L2. And that's what we're going to use. We'll just write out what L1 is again, just so we can remind ourselves. It is equal to MP RP dot cosine theta I minus MP RP dot sine theta, and these should be at time 1, so RP 1 dot. And then for L2, we have here M plus P plus MC R dot, not a vector, R C dot in the I direction. So if we go and set these equal to each other, we're going to have MP RP1 dot cosine theta I minus MP RP1 dot sine theta J is equal to MP plus MC RC dot in the I direction plus 0J. We're going to come back and talk about that 0J in a moment. In fact, actually, we'll deal with it right now. So I said that linear momentum is conserved, and this is not entirely true. Linear momentum is actually only conserved in the I direction. It is not conserved in the J direction. In fact, what we need to actually have, we need to actually come and caveat this. We can say here that linear momentum is conserved in the horizontal direction. So what that means really is that we should actually, instead of having, well, it still is 0 here, but what we're missing is that on the left-hand side, we should actually have that the impulse due to the reaction. So we should actually have here R1 plus R2 delta T in our J direction. And now this is valid. And what we can now go and do is that we can write here that we can set the I direction equal together, and this is going to allow us to find the final velocity of the cart, and we'd also be able to find an expression for this R1 plus R2 times delta T in terms of that J direction. So let's go and do that. So we're going to get here in our I direction, we're going to get MP RP1 dot plus, I left out the cosine theta, and there's no plus there, so that's just an equal to MP plus MC RC dot. And then from here, we can go and we can just directly solve, and this should be RC2. I left that out. Let me go and add that back in here. RC2 dot. We can go and we can find RC2 dot just by directly dividing here, and we'll get, in fact, we'll write it as MP over MP plus MC times RP1 dot cosine theta, and it's going to be, if we want to do our vector, it's going to be in the I direction. That's our final velocity because velocity is a vector. And this right here is then the answer to part A. Now, we didn't ask for this, but I'm going to do it anyway. In the J direction, we're going to have here R1 plus R2 delta T minus MP RP1 dot sine theta equal to 0. And then from here, we can just show that the impulse R1 plus R2 delta T is equal to MP RP1 dot sine theta. That's one of the equations we would need in order to find this reaction. The second one would come from considering the applying impulse momentum purely to the cart itself after we apply it to the package directly. So applying it to the package, applying impulse momentum to the package first is going to allow us to determine those impulses or that are acting caused by the collision between the package and the cart. And once we know what that is, we could then go and do the same impulse momentum principle and apply that to the cart, which would then allow us to gives us a second equation for this reaction, and from there we would then be able to go and compute what each of the reaction forces are. We're not going to do that because that's not what we're interested in. Instead, we're going to focus on determining the impulse created or exerted by the package. So to this end, we're going to consider only the package, and then we're going to apply the principle of impulse momentum. And I'd like you to go and pause the video and give this a shot, and then we'll come back just like previously, and I will go ahead and show you how I would solve this, and you can compare and take some time to reflect as well after that. All right, welcome back. So we're now going to go ahead and we're going to compute the impulse exerted by the package, and then you can compare with what you did with what I did. So to compute the impulse, we consider only the package and apply the principle of impulse momentum. So we're going to consider only the package and apply the principle of impulse momentum. All right, so we can write that out, and we'll get here that rp1 dot vector plus the sum of the forces times delta t, that's our impulse, is equal to mp rp2 dot, which is equal to mp rc2 dot, and that's not a vector, that's just in the I direction. So expanding into the left-hand side into components now, we're going to get that mp rp1 dot cosine theta minus fx delta t, that acts in the I direction, plus we're going to have minus mp rp1 dot sine theta plus fy delta t, that acts in the j direction here, equal to mp, and we'll just leave it as rc2 dot right now. Actually, yeah, we'll leave it as rc2 dot right now, and then we'll introduce it later on. Just to save us from having to write it out over and over. So from here, and this is in the I direction, plus 0j. So now we'll consider the I direction, and we're going to have here mp rp1 dot cosine theta minus fx delta t equal to mp rc2 dot. That's in our I direction. So we can go and solve directly for that impulse, fx delta t equal to mp times the quantity rp1 dot cosine theta minus rc2 dot. And that's our impulse in the x direction. Now for the j direction, we're going to get here minus MP RP1 dot sine theta plus Fy delta t, and that's equal to 0. So we can go ahead and we can solve for that impulse. Fy delta t equal to MP RP1 dot sine theta. So we know that RC2 dot is equal to MP divided by MP plus MC. RP1 dot cosine theta. And then we plug this into the impulse for Fx delta t. And we're going to find here, we can actually pull out well, give me one moment here. So we were able to pull out an MP and an RP1 dot cosine theta. So we're going to get MP RP1 dot cosine theta. And this is going to be 1 minus MP divided by MP plus MC. From here, we can go ahead and we'll find that Fx delta t is equal to MP MC divided by MP plus MC times RP1 dot cosine theta, that's in the x direction, or the I direction, then Fy delta t is equal to MP RP1 dot sine theta. And that is the solution to the second part of the example. You should take a moment and compare with what you got. And then that is the it for this lecture. In the next video, we're going to go and cover impacts and discuss different types of impacts.